Hi everyone, welcome back to chemistry. In this video, I want to continue talking about acids and bases, but I want to start with a different way that we can think about them. And that's using what's called the Brønsted-Lowry definitions of acids and bases. So I mentioned that there were some other scientists who came along later after Arrhenius that had a different definition of acids and bases. And those were two scientists, Johannes Brønsted, who was a Danish scientist, and Thomas Lowry, who was an English scientist. And they both kind of independently proposed these new definitions for acids and bases. And these scientists, rather than considering both hydrogen ions and hydroxide ions, right, H plus and OH minus, like Arrhenius did, they actually just focused on H plus. And this is really interesting because there are actually quite a few bases that don't have hydroxide in them to start with. So it becomes a little bit more all-encompassing. We can think about lots of different reactions as acid-base reactions that we didn't previously think were acid-base because we didn't see that there was hydroxide in our base already. So they said that an acid is a compound that supplies a hydrogen ion or donates a proton in solution. So this might look familiar, this definition, because it's just like the one that I gave you for Arrhenius, right? You could think of it as an acid is anything that donates a proton in solution. So they don't differ so much on that regard, but they do differ on what they call a base. So these scientists said that a base is a compound that accepts a hydrogen ion in a reaction. So any compound that accepts a proton in solution. So what do I mean by this? Let's take a look at this reaction here. And you'll notice we have ammonia. This is ammonia, right? NH3 reacting with water to produce the ammonium ion, right? NH4 plus, the one cation polyatomic ion that I wanted you to memorize, and OH minus, or hydroxide. So on the left, you can see that water is going to give its hydrogen to ammonia. And so if we think about what's happening with that hydrogen, we would call water here an H plus donor. It's giving its hydrogen away. It's donating that hydrogen. And anything that donates that H plus in solution is going to be called a Brønsted-Lowry acid. So water here is acting as our acid. Now, before we knew about the Brønsted-Lowry definition of acids and bases, we wouldn't have said that this was a base, right? Because we don't see that OH minus there. But there are actually a lot of bases that don't have OH minus in them, and ammonia is one of them. So what happens is ammonia is like, well, I would love to take that hydrogen off your hands. And when it does, we can call it a hydrogen ion acceptor, right? Something that accepts a proton or a hydrogen ion. Remember, we use those two interchangeably. And in this case, then, if it's accepting that proton, right, accepting a proton, we would call it a Brønsted-Lowry base. Now, I do want to take a quick side note before we move on, and I want to talk about something called the hydronium ion. The hydronium ion. Now, my question for you is, do you really think that we have these bare protons floating around in aqueous solution? And the answer is no, we don't. What ends up happening is that this hydrogen ion, or this bare proton, ends up attaching itself to water to make H3O+, which we call the hydronium ion. So we've got all these bare protons floating around in solution, and we've also got our water here. And what ends up happening is those hydrogen protons are not happy. They want to attach to something. And so they'll actually attach themselves to our water molecule. And when they do that, water was neutral and now it has an extra hydrogen on it, which contributes to this overall positive charge. And we now call this new thing hydronium, H3O+. Right? 3 H's now, because our proton added to our water, and with a plus because we have an overall positive charge because of those positive charges on those protons. So essentially, why am I telling you this? Whenever you see H plus in an aqueous solution where there's water around, right? Aqueous solution, we can actually use H plus and H3O plus these formulas interchangeably, because wherever you have H pluses and you're dissolved in water, you also have hydronium, and that will become important later. All right, now once an acid has given up a proton, like we saw up here, we saw our water, right, giving up that proton there, or that H plus, the part that remains we call the acid's conjugate base. Because once it gives up that H plus, now it could act as a base, right? So water over here gave up one of its protons, one of its hydrogens, and it turned into OH minus at the end, once it gave away that hydrogen. So we would call OH minus the conjugate base, the part that remains after that H plus is donated. Now, why do we call it a conjugate base? Well, now looking over here, what you'll notice is that we've got some equilibrium arrows here, which means what? Yeah, it means that there can also be a backward reaction, and there is. This reaction is at equilibrium. So just as these two are reacting together and producing our products can back react and produce our reactants again. And if that's the case, right, this can act as a base and steal back one of the hydrogens from ammonium. So we would call it our conjugate base. Likewise, the part of the base that remains after the base accepts a proton, right, when NH3 accepts a proton, now the thing we have left over can act as an acid. So we would call that the conjugate acid, because now ammonium has an extra H on it, and that proton can be donated, and that would mean it would serve as an acid. Kind of weird, but let's try a practice problem. So this says, identify the conjugate acid-base pairs in this equilibrium. Okay, so what's interesting about water, and what I didn't mention before, is that water can act as both an acid and a base. Water can act as either an acid or a base. So above, we saw that water was acting as an acid because per the Brønsted-Lowry definition of acids, it was donating a proton, right? Donating a proton. So that makes it an acid. But water can also accept a proton, right? We've seen that happen. And when it accepts a proton, it becomes hydronium. So in this case, right, if water went from H2O to H3O plus, it had to have accepted a hydrogen. So, and then you'll notice that this whole thing here, it goes from CH3CO2H to just CH3CO2 minus. So what happened here? Well, it looks like from here to here, we lost a proton. And from here to here, we gained, we gained a proton. So which one is our acid and which one is our base? Yeah, this thing is going to act as our acid, right? It lost a proton or donated a proton. Well, donated a proton to who? To water, right? If that's our acid, then our water must be our base. Okay, so this is our acid, and specifically this has a name. It's called acetic acid. Acetic acid. So acetic acid is going to give this hydrogen to water. And when it does that, we form hydronium and something called acetate. And I'll put these are ions actually, right? They've got charges. All right, so we said acetic acid is donating a proton to water, which means water is accepting a proton, right? So this one's our acid. This one's our base because it's accepting that proton. And what does that mean about the right side of the equation? Well, let me clean some of this up a little bit so we have a little bit more space. So remember, the part that remains from your acid is at the end of the reaction is called your conjugate base. So what's the conjugate base of our acid? Yeah, this thing here, acetate, right? Conjugate base. The part that remains after it gave away that hydrogen, right? This is the only thing that changes. We don't have that hydrogen anymore. So that's our conjugate base of our acid. What's our conjugate acid of our base? Yeah, H3O plus, right? Conjugate acid. All right, so let's think about this for a little bit. We said that the thing that's left over after our acid gives away its hydrogen or donates its proton is our conjugate base. Now, if this is our conjugate base, why do we call it a conjugate base? Well, remember, this is happening at equilibrium. So just as we are forming these products, we can also get back our reactants. How do we do that? Well, this acetate can steal back a proton from our hydronium. And when it's accepting that proton, we would call it a base, right? So it can act as a base. So it's the conjugate base of our acid because it can act as a base on the right side of the equation. Likewise, hydronium can say, here, go ahead, take this extra hydrogen I have. And when it does that, it's donating a proton, and we can call it an acid, specifically our conjugate acid, because it's the acid that's created from our base. All right, now, like I said, water can act as an acid and a base from the Brønsted-Lowry definition of acids and bases. So for the following reactions, I want you to determine, is water an acid or a base? All right, well, it looks like water gave up one of its protons to NO2 minus, which is called nitrite, and it ends up going here, right? Bonded to NO2. So water is donating a proton. If it's donating a proton, what do we call it? Yeah, an acid. Because, let's write a note, because it donates a proton. What about here? Is water acting as an acid or a base in this next equation? Well, I'm noticing that we get water turning from H2O to H3O plus, which means that water gained a proton from our acetic acid. So here, water is acting as a base because it accepts a proton. So really important to figure out, to be able to know whether water is acting as an acid or a base. All right, so just as there were strong electrolytes and weak electrolytes, there are also actually strong acids and bases and weak acids and bases. So there are a small number of acids that ionize completely in aqueous solution. What does that mean? Just like we talked about with electrolytes, what happens when we put these acids in water is they break up into their ions 100%. So for example, when HCl, hydrochloric acid, dissolves in water, when we put HCl in water, what ends up happening is we get out H plus and Cl minus. Every molecule of HCl is going to separate or dissociate or ionize completely into H plus and Cl minus. Now again, if we have H2O here and we have protons floating around, we don't just have bare protons. What ends up happening is they bond to that water. So you could also think of H plus as hydronium as well. Right, we use those interchangeably. But the main idea is the same, right? HCl is going to dissolve in water, and every single molecule of HCl is going to separate 100% into ions. And we call this a strong acid. Likewise, a strong base is a compound that is 100% ionized in aqueous solution. So things like LiOH. When we put LiOH in water, it ends up breaking into a hydroxide ion and a lithium ion. Right? Or here we've got NaOH, a sodium ion and a hydroxide ion. They 100% dissociate in water or ionize in water. So for our class, unfortunately, you're going to just have to do a little bit of memorizing for these strong acids and bases. So the ones that I want you to memorize as being strong acids are HCl, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. I don't care if you memorize this last one here. And you'll notice that these look familiar. These are actually the acids I wanted you to memorize earlier in the previous video. So you're not memorizing any extra. All of the acids that I asked you to memorize are strong acids. And let's actually write strong acids. As for bases, a strong base is anything where you see that hydroxide in there. So lithium hydroxide, NaOH, KOH, all of those. I don't specifically need you to memorize exactly these ones, but I want you to memorize that anytime you see that OH, okay, that's going to be a strong base. So memorize that strong bases have OH minus in their name. Now, if anything is not a strong acid or a strong base, then it's a weak acid or a weak base. And what does that mean? That means that the compound is not 100% ionized in aqueous solution. So if I ask you if a compound is a strong acid or a weak acid, if it's not on the list that I've asked you to memorize of strong acids, then it's not a strong acid and you can call it a weak acid. If a base is, if I'm asking you if it's a strong base or a weak base, and it's not, that base is not on this list, then it's not a strong base and it must be a weak base. Another way to tell if something is a weak acid or a strong acid is for strong acids, when you see the arrow for those strong acids, so for instance, HCl becoming H plus and Cl minus, you'll always see that arrow as just a forwards arrow. Why is that? Well, it 100% ionizes in solution. Whereas for weak acids or weak bases, you'll actually see that equilibrium arrow. And if you see that equilibrium arrow, it means that it does not 100% ionize, right? Or in other words, these can back react and you can get back your reactants again. So for something like acetic acid, which we have here, acetic acid is a weak acid. It's not on our list of strong acids, so it's not a strong acid, and we'll call it a weak acid. And we know it's a weak acid because we've got these equilibrium arrows, meaning that once you make some of your conjugate base from your weak acid, it can just go back and back react, and you'll get out that acid again. It doesn't 100% ionize. It's at equilibrium. Both the forward and reverse reactions are occurring, and it's at equilibrium.